So in this situation, they say, given that example right here, what is the tension in the horizontal string? I'm going to ask you a couple of questions. What is the tension, which is just the force, in the horizontal string and the one hanging from the ceiling? Okay. So the one from the ceiling and from the wall. In this particular question, they asked you just the one from the wall, the one that's hanging horizontally, but typically you'd be able to find out this one, and that one. Okay. So if you could find one, you'd be able to find the other one, as you'll see in just a moment. This situation doesn't have any motion, let alone any acceleration. So this sign isn't moving. The whole string connection here isn't moving. So this is a situation where there are forces, but they're in equilibrium. So if you think of that, F net equals 0, which really means that they're in equilibrium. If they're in equilibrium, then the sum of the forces have to equal 0. So just like we did with our lab when we were pulling on the fishing line, add up the force vectors and they should equal 0. So here are all the forces acting on all of those ropes. This is called a free body diagram. It's a diagram of all the forces acting here. I had one acting up this way, one acting this way, and one acting this way. It's really important to draw the free body diagram first before you get into trying to solve the problem. I'll call this force right here tension 1. I'll call this force here tension 2. And I'll call this force right here, actually this force down, is what? Yeah, gravity on the sign. Yeah. So that's just the weight of that sign. So we've got three forces, and in fact we've got some good geometry here. We've got 90 degrees, thank goodness. And if you take a look, I had 50 here from horizontal. If this is horizontal and this is vertical, that has to be 40 degrees off of vertical. So I got 50 here, 40, and if I just make this continue from horizontal, this has to be 50 degrees. That is an alternate interior angle, this 50 and that 50. So it's interior here, and on the alternate side, it's 50 degrees. Do you guys remember that term from geometry at all? So this one has to be 50, and by a couple different ways I just showed that this one here is 40. That's going to be important when we actually put the vectors together. Okay, so 90 degrees here, and then 50 or 40, whichever way you look at it. So I've got all the forces, and that's the first step to do. Now once you have the forces, you add up all the vectors, and they have to come to 0. So they close. It makes a closed triangle, and that's the next step of the problem. So we've got a free body diagram, which is great. And now we're going to go one step further and make the force vector diagram. So now, sum of force vectors equals 0. You use this free body diagram to help construct a force triangle that's closed. It's not open. So all of the vectors will add up to 0. What that means is they all come back to the starting point of the first vector. So if I've got T1 starting right here, and I go up, There's T1. Right where it ends, I add T2, and T2 goes right over horizontally, and weight hangs vertically. So this one can only go horizontally far enough so that this one would hang vertically. So there's the weight vector. Here's the T2 vector, just to clean it up a bit. Here's the T1 vector. So T1 goes up this way for sure, and at some point, whatever you want in terms of distance, you could stop it, but then this one has to come off horizontally. This one comes off horizontally, but only to the point where this one would hang vertically and then come right back down to the beginning of the T1 vector. So it's a totally closed triangle. So this is a triangle of all the force vectors, showing that they're zero. They come right back to where the T1 started. So T1 plus T2 plus weight 1 adds up to 0. And now you just go and take a look at the geometry of what you had up here. The angle between T2 and weight 1, between T2 and weight 1, had to be 90 degrees, so we drew it that way. Where T2 ended, which was horizontal, we dropped a vertical line. So that is 90 degrees for sure. This T1 goes off at an angle that's equal to, between T1 and the weight, is 40 degrees. So between vertical and T1 is 40 degrees. So that one here is 40. If that's 40 and this one's 90, this one has to be 50. And you guys can even see that right up here. Between T1 and where T2 would go off, it would be 50 degrees. So with just normal trigonometry, I can find out what these sides are because I know this side already. This weight 1 is just mass 1 times 9.8, which is just 0.75 kilograms times 9.8, which is, what is that? 7.35 maybe? I just winged it. So you've got one side here, 7.35, and you got geometry, and you got a 90-degree angle, so you don't even have to use sine law or cosine law. You can find out what the other sides are, and that's what the question was asking. What are the other sides? So can you guys crank them out right now? And let's agree on our answers. So everyone should have a calculator of just working away on it. You can use sine, cos, or tan, whatever you want to do. Or whatever way you want to do. But you should be able to crank them out no problem. Anyone got T2 yet? T1?
T2, I got 4.72.
Sounds good. And T1? Anyone else get 4.72?
Oh, offer, that's off.
Is it? Okay, again, you can use whatever you want. You can go sine 50 is W1 over T1, whatever you want to do, opposite over height. But no matter how you do it, you should get the same answers. Which one? T1? Okay, T1 has to be bigger than weight 1. So 7.35, you know it's got to be bigger than that because it is the hypotenuse. And, sorry, Nick, you got
9.59.
Okay. Thank you. Looks realistic. I haven't actually done it, except in my work from before. Anyone else get 9.59? Nice. And it looks like it makes sense because it's the hypotenuse. T2, hard to tell, but you know it's not going to be exactly 7.35.
6.17.
6.7, sorry?
6.17.
Oh, 6.17, yes. Same as mine. Okay, perfect. And Nick, if you can.